Okay, day 7 is our start of our foray into kinematics. That's when things start getting more mathier, i.e., more fun, funner, whatever the word is. We'll say funner. Okay, coordinates. So the whole purpose of the lab was to express and get you understanding with coordinates. Um, Spatial coordinates, we experience a three-dimensional world. We have north, south, east, west, and up, down. Also called the right-hand Cartesian coordinate system. Um, and for example, you can express. The whole purpose of having a coordinate system is you can express something with respect to the other direction. And as you guys found out, south, there's a little space there, probably need to get rid of that, is the opposite of north, meaning south is negative north. The example I like to use is if someone asks you and you live in Wichita and they go, well, where is Newton? And you could say 30 miles to the north, or you could say 30 miles to the negative south. Either one is correct. The big issue with that is when you're programming or coding anything, just putting a negative sign just flips the entire operation in the other direction, and so that's why it's perfectly acceptable. Probably shouldn't be used because it can lead to confusion, but it is correct. So I'll give it that. Oh, I already mentioned, yeah, we use what's called the right-hand Cartesian coordinate system, where we have x right here, y, and z. We're only ever going to deal with one dimension for what we do. Even physics 213 and even 313, they only deal with two dimensions at best. They rarely get to three because it gets a bit more mathier. Describing positions. It takes two coordinates to describe the position of our objects, because you have to have one to base the other one off of. And more importantly, an origin is going to be needed so that we can fully describe the position. Because if we don't have an origin, this person might be 30 meters away from me, but where am I on the surface of the planet? I know that I'm 30 meters away from this other person, but I don't know where I am on the planet. So it's good to have a base of origin that you can operate. Another good thing, I always bring this up every year, is in 2063 on April 5th, we're supposed to make first contact with the Vulcans in Bozeman, Montana. I've been there. They don't have anything celebrating this monumentous occasion that hasn't happened yet. But I bring this up because if we do discover an alien race, it's going to get a little tricky to say where their planet is. For instance, most of the stuff in our solar system is based off of Sol, our sun, in the center. And if Vulcans have some sort of similar setup there, they would use their star to map everything out. So we would need some sort of origin. Now, assuming that we meet an alien race in our galaxy, we could use Sagittarius A star at the center of our galaxy. It's a big black hole. And then we can both give our coordinates with respect to that origin. So everybody's got a slightly different origin. And that's why coordinates are kind of important, because you're going to have to convert from one set of coordinates to another. Another good example is... there's a really good movie about it too, and I can't recall it. But if you have a train that goes from China into Mongolia, they literally have to stop and switch out the wheels because they have a different standards for the width of the wheels on the train tracks. And they would need some sort of conversion to make sure that they get to the right width. So it's good to have some sort of origin so that you can start to convert from one form to another. And that's why we had to do all those examples with origins. Position, distance, and displacement. Position is the location of an object with respect to a given coordinate system. Position is closely related to, say, football. Your position would be what yard line you're on. It's a little harder to describe, but at least with football, because there's a 50-yard line, and then there's the home and the away turf, or so to speak. But that would be a good position. The distance is the sum of all incremental lengths traveled during the motion of the object. So if a person runs down for 10 yards, that's the distance they traveled. Now, displacement is the difference in length between the object's initial and final position, and it must include a direction. So the distance is, well, he ran the ball 10 yards. Okay? Well, I have been in a football game where somebody on my team ran the wrong way, and subsequently got us a safety because he scored, so to speak. But yeah, you may have run 10 yards, but what direction did you run 10 yards? 10 yards is the distance. That direction is what makes it a displacement. And then position is where he ended up in the end zone. So that's my example I use. So let's just say we go from A to B. The distance is going to be around 300 centimeters, and the displacement would be a positive 300 centimeters. In this class, you could just put 300 centimeters. We're going to assume that it's already positive. Otherwise, you'd put a negative there. Let's say we go back from B to A. The distance is still 300 centimeters because it doesn't care about what direction you went. The displacement is negative 300 centimeters because now we're going back towards the origin. And the overall distance traveled was 600. And the fun fact is the overall displacement is 0. So that leads to more interesting things, like if you were born and die at the same hospital, you may have a lifetime distance of millions of miles, especially like, let's say you're a pilot, but your actual lifetime displacement may only be a couple hundred feet between like where the people give birth and where people die, or maybe just all the same in the ER. If you die in a town different than where you were born, like for me, example, I was born in Pittsburgh, Pennsylvania, and if I die in Wichita, then I'll probably have a lifetime displacement around 1,000 miles. But a lot of people don't. They have a very limited lifetime displacement, even though they travel a lot. So the overall displacement does care about your beginning and end points and doesn't care about anything in between. This class, as I mentioned, will stay in one dimension. Instead of D for position, we use X, XI for initial position, XF for final position. And then our displacement would be delta X is equal to XF minus XI. Most of the time, we're just going to use X for position. We don't generally have two different positions. Or rather, we just kind of assume we kind of draw conclusions and we end up just using an X instead of XF minus XI. And I'll talk about this probably in later videos, but for the most part, you're just going to use X for position. And finally, time. Time is also a coordinate system, and it's usually instantaneous. We express it in seconds, hours, etc. There's all sorts of things you can do. And time can be negative. It indicates that it occurred before the origin. So going back to my Vulcan example, April 5th, 2063, we're, 2021? So what is that? 40. Oh, God, I'm getting old now. God, it was 50. It was negative 50th anniversary. I feel like yesterday or just a couple years ago, but we're negative 42 years because it hasn't happened for 42 more years. So it occurs before the origin, and then finally time. This is a very simplified version, but time and space are intertwined actually, and it's really really complicated. Time and space can be warped. This is a best little example. But this is very three-dimensional viewing of what's actually four-dimensional, so you have to take it with a grain of salt. But any type of massive body will actually warp space and henceforth time, since it's called space-time. So that has kind of interesting implications. That means that time runs slower when you're closer to a massive body. So that clock, say, a clock in the center of the Earth would not be in tune with a clock in orbit, just because it's closer to the center of gravity of the Earth. And so we don't have to deal with it too much. I mean, they have to make some adjustments called general relativity. They also have to make adjustments due to special relativity, how fast you're going. But it does have to be utilized in very, very, very specific applications, and if you want a very, very accurate time. It also does warp space-time around more massive bodies such as the sun. That gets into a whole other ball game. But like I said, time is really complicated once you really get down to it. And finally, I said finally last time, but I kind of jumped the gun, I suppose. Duration, that's the length of time required for a process or series of events to be completed from beginning to end. We use T for time, so TF and TI. Duration is always going to be positive, much like distance. But time itself could be negative, much like displacement. So you can kind of keep those two together. It should work out pretty well. All right, that is it. I shall see you in class today because you're taking a test. Fun.